Hello, folks. So my name is Will Lovett. I am the technology manager in Arm's software division for the compiler teams. So I look after the GNU, the LLVM, and the functional safety compiler teams that we have here at Arm. And today I'm talking about Arm Toolchain, which is a set of new compilers that are coming out of the LLVM team. So we've just, in the last month, released Arm Toolchain for Embedded 20, which is our new compiler for embedded and bare metal development, and also Arm Toolchain for Linux 20, which is our new compiler for native x64 Linux, cloud, and HPC development. Now, this is quite a big milestone for us, partly because we don't release brand new compilers very often, and partly because they are now 100% open source, which is a huge transition for us that's taken a long time. So I'm going to spend some time today talking about these tool chains from a developer perspective, so what it's taken to get to this point, where you can find the code, how you can engage with us. Then a bit of time talking about the user perspective of what these compilers are and what they can do. And if we have time, I'll look forward to where the LLVM team in Arm are going to invest over the next year. Okay, I'm pretty sure most of the people in this room know what LLVM is, right? So it's an open source framework for building compilers, and lots of compilers are built from it. We've been involved for certainly much more than half of the 22 years that LLVM has been going as a project. So let's skip forward. This is the team, who are now quite big. There are 67 people, including sort of management and supporting roles, in the LLVM team in Arm, which makes it the biggest individual project within the software division of Arm. About 2/3 of us are in Manchester in the UK. Sorry, 1/3 are in Manchester, 2/3 are in Cambridge. And we're from a bunch of different backgrounds. This is what AI thinks our office looks like, which it doesn't quite yet, but we'll get there. So this is an attempt to talk about the level of engagement that we have in upstream. So we represent about somewhere between 2 or 3% of the active community in LLVM, but we're responsible for about 6% of the activity within the community as a whole. And this graph is the most active individual contributors within the LLVM ecosystem, excluding bots, based on the activity like interaction with issues and pull requests and so on. And the highlighted people are members of the Arm LLVM team. So 8 of the top 100 contributors in LLVM are from our team. For context, to make it to the very bottom of this list, you need to be interacting with the community about 550 times within a year. Okay, so if any of you were here at my talk last year, you may recognize this slide. This is a timeline of our engagement with LLVM. So we started with Arm Compiler for Embedded in 2014, where we were based on LLVM with a bunch of downstream Delta. We had a linker and libraries that came from Arm Compiler 5, which were purely downstream. A few years later, Arm Compiler for Linux was our first entry into the HPC and cloud space, which is mostly upstream components, except that it had a large downstream debt for SVE, because we'd developed that whilst the architecture was still private. And we didn't have the LLVM flying front end yet, so we had a front end based on the PGI compiler. Shift forward another 4 years, and the embedded team made a project for making an open source LLVM-based embedded toolchain called LLVM Embedded Toolchain for Arm. And that brings us to today, where we now have Arm Toolchain, which is as I said, 100% open source. So we've got rid of all of the downstream delta in both compilers. We've been investing heavily in the Fortran front end, so the Flang front end in LLVM is now suitable for use, which means that we believed that we could build our compilers purely from open source components, which my role is somewhere between engineering and business, and I absolutely love that this is a decision that makes complete sense in both sides. So from an engineering perspective, you want to enable as many people as you possibly can, and open source is by far the best way to do that. And from a business perspective, being able to, by enabling people to get the best out of ARM across all the spaces where ARM plays, then that adds value to ARM's proposition of selling hardware. So we've shifted names slightly. Whenever you see ARM compiler, I'm talking about the old stuff with the downstream dep. Whenever you see ARM toolchain, I'm talking about the new thing. So in order to build a toolchain, you need a recipe to do it. And we've taken upstream LLVM, and we've made a new GitHub repo that is a mirror of that. So it tracks LLVM trunk constantly. And to it, we add a few things that are different from public LLVM. And I'm going to talk about why we think we need those differences. The first one is that you need scripts to integrate your toolchain and build scripts and CMake files and some of the documentation and things like this. That's going to live forever. Where possible, we'll feed back anything that's useful to the LLVM community, but mostly that's like a separate subdirectory that we add on and we will maintain it forever. Then three other things that are hopefully mostly not forever is sometimes a partner will have a critical need for us to fix a bug, and we might not wait for that to get all the way to upstream and to get a new release out. So we might choose to pick up critical changes. But when we do that, we'll mark them as experimental, and we will always favor the upstream version, so we will switch to that as soon as it's available. Then we expect to need to maintain our toolchain for longer than LLVM does. So we may choose to backport things to older releases to support our users. And sometimes we anticipate that we might sometime have the need to show good performance on some benchmark with an optimization that the community don't want to accept. And if that were to happen, we reserve the right to allow ourselves to take that optimization. But when we do that, we will always guard it behind a default off flag, so that the default behavior of the toolchain will always match upstream LLVM. It has the same license as LLVM. It's all Apache 2 licensed. And you'll notice that I said it was release 20, so that matches the LLVM 20 release. It's built from the LLVM 20 release branch. And our release cadence will be the same as LLVM. So we will always make our new releases usually within a month or so of the main LLVM release. We welcome pull requests, and we've got issue tracking in GitHub. You can either raise them directly with us, and then we'll deal with them, or if you think that it's an issue with LLVM, then you can raise it with the LLVM community. And we, as I said on the previous slide, we're very active in that community, and we will notice and pay attention to that. I have an example from last week of just how powerful that is compared to having a separate downstream process, where a partner was emailing me about a missed opportunity with our new compiler. So number one, I could use Godbolt because it's got up-to-date LLVM. So this partner and I could go back and forth and reproduce the issue and understand it. And number two, because I've got a bunch of developers who are very active in the LLVM community, if they have to spend time with community process and also spend time with ARM development process, then that feels super inefficient. Whereas if I just raise it, as I did, as an upstream issue, then my team notices it straight away. And number 3, perhaps my team don't even need to fix it. So in this particular case, the same day, somebody from another ARM partner saw this issue, fixed this issue, raised a pull request. Somebody at ARM happened to review it, and within a day of me raising it, it had been merged into upstream and fixed, which the amount of time it takes to do that with downstream code is relatively huge. Okay, so let's shift to the user perspective, so what these compilers are. So first is Arm Toolchain for Embedded 20. So this is our compiler for embedded development. In order to do that, you need a C library, and this compiler uses picolibc by default. So again, we've shifted away from having our own proprietary C library and using open source ones. It also has support for newlib and newlib nano because they're heavily used in this space. And we're starting to invest quite heavily in LLVM libc. We think that this might be quite a good long-term option for a bare metal embedded C library, and quite well suited for doing functional safety qualification of as well. So this is something you'll see us invest in quite heavily over the next few years. It has C++ support at the same level as ARM compiler for embedded had. And one other big advantage of using, in particular, the LLVM linker is it means that we're immediately compatible with new security features, such as sanitizers, that are being developed quite heavily in the community. And we can pick those up effectively for free and make them available to our users. Finally, there will be a professional supported version of this. So ARM Development Studio users will get a version of this that is professionally supported, but it will be functionally identical to the free version. And this is available for free today to download from GitHub. It has no licensing technology or anything holding you back. You can just use it for anything you like. It supports Linux, Mac, and Windows hosts. Okay, let's look at the performance of it today. So now remember that ARM compiler for embedded, we've spent a very long time making it the best compiler we can for microcode and bare metal embedded development. So this is where we're at today in terms of the performance of the new compiler relative to this one that we've spent a long time optimizing. I've only got a couple of data points for A50 for Cortex-A processors because reasons, but you can generally expect that the code quality on A profile should be about the same for both. Now for M profile, for newer cores, the delta is less. So for older, like M0 development, there's definitely a performance delta, and you might be best using ARM compiler for embedded for now. By the way, we've just made the last release of ARM compiler for embedded, so that's also kind of available to users and will be for at least 5 years. But we'll be working on reducing this gap especially for newer M profile cores such as M55 and M85. Okay, switching over to the Linux compiler. So this is for cloud and HPC development. It replaces ARM compiler for Linux, which was our previous compiler for that. For C and C++ users, I can recommend it for all of those users. It has very mature support for C and C++ standards and for OpenMP in C and C++. For Fortran, as many of you will know, the LLVM project has been building a Fortran front end. We've been heavily involved in that. That's very close to being production ready, in my view. Use of that with OpenMP at the LLVM 20 release had support for OpenMP 2.5, but that's progressing extremely quickly. Like in trunk right now, it's moved forward to 3.1 with some OpenMP 4 features being implemented right now. We're considering that experimental, but mostly because there are features that you could use that aren't yet supported that it will crash on instead of gracefully exiting. I'm hoping we might remove the experimental badge of that in 21 in the fall. But I'm very confident that by the time we get to 22, then it will be an excellent compiler for all users on ARM. There is one functional difference here with upstream LLVM, which is LLVM has a flag called -f-veclib that allows you to supply a library of vector variants of math routines. And that means that during vectorization, if you have a loop with sign in it, then the compiler can use those vector variants to vectorize that code. So that's available in upstream today, but in order for that to work, you need that library to be available. And because of the way our installer works, I know that library will always be available in Arm Toolchain for Linux. And therefore, I enable this flag by default for all users, because it's almost certainly the most useful thing to do. We have a plan to upstream some vector variants into LLVM libc this year, and so I'm hopeful that we can get it to the point where we can do that for a standard build of Clang. It's available for Linux, obviously, and one other shift is that instead of downloading this from developer.arm.com, our default install mechanism now is using a Linux package manager. So there's some instructions you can follow. There's a one-time setup, and then you can say apt install Arm Toolchain for Linux. On the performance side, this is a set of the HPC workloads we most care about at the moment. There's some real-world workloads. There's some mini apps and things. You can see a split of C++ and Fortran ones. And the general message here is that we're about on par. There are a few things that we'd like to invest in and make better, but the performance of the new Fortran front end in particular is actually pretty good. Okay, what time check? I've got a few minutes. So now I'm going to look forward to the investments that the ARM team are expecting to make over the course of this year. This is a tree map where the size of these boxes roughly represents the size of the investment I expect the team to make over this year in a bunch of different spaces. And I'm going to focus in on a couple of these. So firstly, kind of big A-profile performance work. So this is our biggest single box of work. And it splits roughly into three different types of work. We do work to make benchmarks faster. We do work to make real workloads faster. And we do work to teach LLVM to be able to make use of features of the architecture, such as SVU2. So this list here is the set of things that we've either completely enabled or have invested quite heavily in enabling over the course of the last year. And we'll continue to invest in more in making sure that LLVM can make the best use of SVU2. And then this may be a little hard to see, but this is the last 8 releases of LLVM and their performance on spec-int over time. And the key takeaway here is that we've been achieving about a 2% improvement in spec-int consistently every release, to the point now where I think that LLVM is an excellent compiler for spec, and there isn't that much of a meaningful gap between this and commercial compilers from other architectures. Our investment in spec 2017 is probably going to taper off at this point, and we're going to turn our attention to the next version of spec, which we've been part of the committee for defining what that is, and we expect it to be released maybe towards the back end of this year, but more likely sometime next year. And so we've started optimizing LLVM for those new benchmarks already. Second one is also about performance, but this is particularly about Bolt and profile-guided optimization. So Bolt is a post-link optimizer within LLVM, and both it and PGO can be very useful for things like cloud workloads, so things like databases and web servers and Clang itself can see some big improvements by taking a profile, and in the case of Bolt, you then rearrange the execution binary. Yeah.
What does mean the CS PGO?
Context-sensitive PGO is a different kind of PGO within LLVM that copes better with passes that rearrange the basic block structure of. So it's a newer PGO technology within LLVM, so the graph here shows the amount of speed up you can get if you take Clang and optimize it to optimize Clang itself. Now, this is both representative of the kind of benefits we're seeing on some other cloud workloads, but it's actually immediately useful in and of itself, because if you're a large cloud vendor like AWS and you have a whole load of open source CI of lots and lots of open source projects running on your cloud, then reducing compile times actually reduces the dollar cost of supporting those open source projects. So making the compiler faster is actually an energy saving thing. Okay, that's what I wanted to say on that one. And then just a splattering of other points about some of the other investments we're making, about things that the ARM lines of business care about. In the bottom left, if you went to the keynote Tuesday, with John Thompson. Yeah, yesterday. Okay. Then you'll have heard John Thompson talking about Cortex A320, which is our new tiny A-profile V9 core. This is quite interesting for a compiler because it's relatively in order. Like almost all of the performance optimization work we do is on the really big cores. And code scheduling and unrolling and therefore register handling are really interesting challenges on very small cores. So we're going to invest a bunch in that this year. In the top right, we are intending to make a functional safety qualified version of Arm Toolchain for embedded for the automotive space. So one of the reasons we're choosing LLVM libc in the long term is we think that we should be able to make a qualified C library using it. And then there's a few other features that we'll be investing in to make LLVM suitable for that space. And then I've already mentioned that we invest heavily in Fortran and OpenMP. The first job there is to get this new toolchain to the point where we can recommend it for all HPC users. But then we'll continue to invest in Fortran and OpenMP going forward. Okay, that's all the slides I had. Thank you for your time. Any questions?
Which C++ you link by default with the toolchain for Linux?
For Linux, we'll use the system one by default. Yeah.
Is there an option to use different C++?
Yes. So as there is in open source LLVM, yeah. We're not heavily testing that at the moment, but I don't have any reason to think it wouldn't work.
About the LLVM embedded toolchain,
Mm-hmm.
is it available on Windows and ARM, the binary release?
The binary release is, I think,
Because it mentions Windows in the supported OS, Mac OS, Linux, Windows.
I would have to double check. I think it's a universal binary, but I would have to go to the GitHub and check. But yeah.
The native Windows and ARM tools for running an emulation.
Well, I get that that's the question. I don't recall the answer offhand, so I can check.
And about your binary releases, are you using the same upstream scripts, or there are some other scripts on top of the upstream scripts?
The latter, because we also, we also pull in picolibc and build it and make it available, and choose a default target and choose to use that for the embedded compiler. We choose to use the picolibc that were built by default. So there are some changes to CMake scripts, but all of those are available on the GitHub.
For ARM-PL, is it the same as the libm library, or if we want to make use of that in C libraries, like do you demonstrate everything works under the hood from Clang, or do we need library changes?
Sorry, could you repeat?
For ARM-PL,
Yeah.
is that the same as libm?
The main purpose of ARM-PL is to provide BLAS, LPAC, and FFT libraries for HPC, but also included in ARM-PL is a library called libamath, which has a bunch of vector variants. The function names of them are different to the libmvec ones, but they are actually the same. In fact, a lot of the implementations of them are identical, but it's basically the same thing.
And at some point, if it's an LLVM, does the C library or the libm from, like, say, for example, Android, does it automatically get the vector versions, or do we need more?
We would need to do work to enable it on Android, but one of the reasons we want to put it into LLVM libc is that should then make it possible that the Android compilers could build those in. The other option would be to enable it in Bionic, which isn't done on AX64 today. But the routines to do that enablement are all fully open source with a permissive license under the ARM optimized routines GitHub repo. So anybody could do that today, but we haven't done that yet.
So, which is the strategy regarding LLVM releases branch? Do you sync with them? Do you track them? Or do you cut on a specific commit and create a branch?
Yeah, no, we release from the final tagged version of the LLVM release. So we're going to lean quite heavily into the release process to make sure that there are no critical defects in there for us. Occasionally we might miss something, and then maybe we'll add something on top. But our goal will always be to release from something that's identical to the release branch of LLVM. Okay, thank you very much.